start our discussion for the PMOS circuit. Okay. Before starting our discussion of PMOS circuit, I want to add two more points. First point is basically, say, uh, if we have selected a particular VG value, right? Particular VG value is selected, and particular VI is there. So we have a finite resistance for this case. Say if we have a high resistance, we want to decrease this particular resistance. We have the possibility of what? If we increase the W by L ratio, we can have more current or the less resistance, right? So this is the one possibility. Other thing I want to add is, so in this circuit we have discussed for this particular region that resistance of that particular MOSFET is dependent upon the input value, right? So if input value is more, we are getting more resistance from the MOSFET, right? If resistance is more, based on the bandwidth analysis we have done for the RC circuit, if resistance is more, bandwidth should be less. If bandwidth is less, we are getting basically more distortion. So bandwidth is less, distortion should be more. So that is what plotted here. So this is the issue associated with this particular MOS. Now let's move to the analysis of PMOS. So first draw the circuit here. Let's draw the circuit here. So here, first I will draw the basically PMOS here. So in the PMOS, PMOS circuit, remaining things are the same. Here is the holding capacitor, and this is the V output value, and this is V input value, right? So this is the circuit. And this, what should be the chain? Basically, if this should be Q, this should be the Q bar. Clock pulse should be inverted. If this is Q, if this is Q, you have to apply Q bar in this particular circuit, right? So, and this, by the simplest analogy, what we have discussed earlier also, and we have analyzed for NMOS, that NMOS easily transmits the low value, or it is a good transmitter for zero, logic 0. Logic 0 is easily transmitted from the NMOS circuit, and similarly we have discussed that PMOS logic 1 is easily transmitted from PMOS circuit, right? So remaining things are same. You will get same issues, basically the change in resistance, the change in input voltage, whatever we are getting from NMOS, same is for PMOS also. But the advantage is PMOS will effectively transfer 1 and NMOS will effectively transfer 0, right? So we want to transmit both the logics 1 and 0 effectively, so the best possible option is to create a transmission gate. Transmission gate is basically the combination of NMOS and PMOS both, right? So in this circuit, say two MOSFETs are combined in this manner. Say if this is NMOS, this is PMOS, meaning they are the same. There is a holding capacitor CH here, and here the output voltage, right? So here clock pulse applied should be Q, here clock pulse should be Q bar, this should be the input voltage, right? So from this we can achieve good logic 0 from this side, logic 1 from this transistor. Let's draw that conductance curve VDD, right? This should be good, right? So for the conductance, we have discussed when the input value is less, you can have more conductance, and when the input value is increasing, you can have less current. Basically, the conductance is decreasing. So if the current is conductance is less, means this value should be somewhat VT, threshold voltage, and this is VDD, right? So this is the case for NMOS. Similarly for PMOS, we can have the reverse relation, right? This should be the PMOS for the conductance curve. So somewhat the effective conductance received from this transmission gate should be the combination of these two. So this should be the effective conductance from the NMOS and PMOS combination, basically the transmission circuit. So this is the effective transconductance which can be achieved by other conductance which can be achieved by the transmission gate, right? Let's move on to the slide what we were discussing earlier. So let's consider the first case here. What is happening here is basically when the gate command, basically GC, which is mentioned as gate command, is the gate voltage basically. So considering the case before the T naught, V output means capacitor is charged before the T naught and the gate voltage is 0, right? Under this condition, and when the input is 0, right? So at the instant of T naught, when gate command or the gate voltage is increased to VDD, if this value is increased to the VDD value, what is happening that both the gate and source and gate and drain voltages are basically equal, right? So if both the gate and source gate and drain voltages are equal to VDD, the transistor will be in saturation mode. Now, the output voltage after this condition will start to fall due to the discharging, and due to the discharging process at the point when the output voltage is equals to VDD minus VT's threshold value, the transistor will go into the triode region. Right? So in this triode region, capacitor will discharge totally and it will take the output value to the 0. Right? In the second case, let's consider that the gate command, basically the gate voltage is low, 40 naught, and the output voltage at the capacitor, or the voltage present at the capacitor is say 0. Then the VDD is applied to the gate. The gate will turn on, right? The gate is turned on. VGS. VGS is what? VGS is equals to VDD. VGS equals to VDD, right? VGS because at the gate VDD is applied and the output is 0. If this value is 0, the VGS is VDD, right? Now after that, watch the value of VDS. VDS should be 1 because this voltage is 0. So if VDS is 1, VGS is VDD. So under those conditions, if you analyze, the device is in triode region, right? What is the relation for triode region? VDS should be less than VGS minus VD. So if this value is 1 volt, it is VDD minus this. So this particular VDS is smaller than VGS minus VD. Under those conditions, the MOSFET is in the triode region, and so under those conditions, gate is on. Whatever voltage is present at the input will be transmitted to the capacitor, right? So from this analysis, when the input voltage 0 is applied, you can get or you will get basically 0 at the capacitor, right? Similarly, when V in is 1 volt, right, V output will follow exactly the V input voltage, right? So when you just start basically transmitting at the time, this particular capacitor will charge up to 1 voltage. So in this manner, it will act as a switch. Means when you apply a 1, you will get 1 at the output. When you apply a 0, it will give you a 0. This is some other way of analysis. So if you don't want to analyze this, the best way, whatever I have discussed in detail, it is the easiest manner to analyze these sample and over samples, right? Both the analysis are somewhat same. Second, you can consider this as when the DC voltage is applied at the input, and while we have analyzed AC and DC both during the circuits what we have discussed in these analysis, right? So this is the discussion for switches, what we have discussed till now. All the discussion related to the distortions, related to the change in the resistance across this particular MOSFET with respect to the input voltage, and the nonlinearity due to those resistive behavior, or the nonlinear resistive behavior which is dependent on the input voltage and all this, right? So this is the total discussion regarding the switches.